Hello everyone, in this section we will focus on reactions of alkynes. Just like alkenes, a characteristic reaction of alkynes is a pi bond acting as a nucleophile uh, and a new bond will form between this nucleophile and an electrophile. So pi bond of an alkyne will attack the electrophile, and a new bond between a carbon, one of these carbon atom, and the electrophile carbon atom will form. So because of this, alkynes undergo many of the same electrophilic addition reactions which we saw in alkenes. So let's take a look at all the characteristic reactions of alkynes. Addition of 1 mole of bromine to an alkyne gives a dibromoalkene. This addition process is a stereoselective process, and bromine adds to alkyne in anti-stereoselective manner. For example, if we start with 2-butene and we conduct addition reaction with bromine, the end product will be 2,3-dibromobutene, and the addition will take place in anti-stereoselective manner. So one Br will be up here, the other one will be down here. So this is anti-stereoselective addition. This reaction takes place in presence of acetic acid and lithium bromide. Chlorine also undergoes similar addition, but it is slightly less stereoselective than bromine addition. Addition of second mole of bromine to the same product will give rise to a tetrabromoalkane product. So in other words, if we start the reaction with 1:1 mole ratio, we will end up with a dibromo product. But if we have excess of bromine, then the dibromoalkene will react with additional bromine to give rise to tetrabromo addition product. This tetrabromo addition product will only form if we have excess of bromine. But if we start the reaction with 1:1, then our end product will be alkene. Addition of bromine to an alkyne follows the same type of mechanism as it does for addition of alkenes. In first step, the pi electrons of triple bond attack the bromine. So this will be a nucleophilic attack. The pi electrons act as a nucleophile and bromine act as an electrophile, and this will result in an intermediate which is resonance stabilized, and it has a bridging brominium intermediate component in it, and in the second step, the bromine nucleophile will attack from the opposite end of the bridge, and the end product will be the dibromoalkene. Alkynes undergo regioselective addition of either 1 or 2 mole of HBr or HCl to give us hydrohalogenated product. Depending on the ratios in which the HCl or HBr and alkyne are mixed, we may get a monobromoalkene or a dibromoalkane. For example, if we react propine with HBr, 1 mole of HBr, we will get a Markovnikov's addition product in which the hydrogen will go to the carbon atom with more hydrogens and bromine will go to the carbon with lesser number of hydrogen and one pi bond will break. So our product at the end will be a monobrominated alkene. However, if instead of 1 mole we start the reaction with 2 moles of product, or sorry, 2 moles of HBr, then the product obtained in first step will continue one more hydrohalogenation step, and in this step one additional pi bond will break and we will get another Markovnikov's addition product which will give rise to a dibromoalkane. As you can see in both these products, addition of in both first and second step is regioselective. The HBr adds to the unsaturated bond in Markovnikov's addition rule. So they follow Markovnikov's rule. So it means that the hydrogen part of the addendum, which is HBr in this case, will go to the carbon atom which already has more number of hydrogens, and the other part will go to the other carbon atom. HCl also react in similar manner with alkynes. The mechanism of hydrohalogenation of alkynes is quite similar to the one which we observed in case of alkenes. In this reaction also, the pi electrons of the triple bond act as a nucleophile, and first step involves the attack of nucleophile to HBr, resulting in formation of a bond between carbon atom and hydrogen. This will result in formation of a carbocation, and in this case we get a secondary vinylic carbocation. Vinylic group has a structure in which we have a carbon-carbon double bond. So this group is known as vinylic group. Vinylic group is a common name for ethene group, ethene functional group. So as you can see that this carbocation also contains a vinylic part, so therefore it's known as a secondary vinylic carbocation. We know that secondary carbocations are more stable than primary. So this will be our reaction intermediate after step number 1, and this step will also generate a bromide ion. This bromide ion will act as a nucleophile in the next step. In the second step, bromide will attack the carbocation site, and it will result in formation of a bromoalkene product. If we use second mole of HBr, or if we use excess HBr, then the product obtained in previous step will undergo one more hydrohalogenation addition reaction. In this case, the product obtained in the first hydrohalogenation process will act as a nucleophile, and the pi electron from the alkene will attack the electrophile HBr, resulting in formation of a carbocation. There are two possibilities of carbocation formation. One possibility is that if the carbocation forms on number 1 carbon, in this case it will be a primary carbocation, and we know that primary carbocations are not the stable. So therefore, this process will be slower because the product is not very stable. On the other hand, the second possibility is that the carbocation forms on the number 2 carbon. In this case, we will get a secondary carbocation, and we know that secondary carbocation is more stable than primary, but there is additional stability factor also. The presence of a bromo group on the carbocation carbon will enable it to form a resonance structure. So therefore, in this case, the carbocation is a resonance hybrid of 2 structure, and we know that more resonance structures means more stability. So therefore, in this case, the reaction step will be much more faster, and hence the major product is obtained from this addition, and the product obtained from primary carbocation is negligible. The secondary carbocation formed in this step is then attacked by the bromide nucleophile to give rise to a dibromo alkane as our final product. Just like alkenes, alkynes also undergo hydration reaction with water in presence of an acid catalyst. If we recall, alkenes show a Markovnikov's addition product when water is added to an alkene. So for example, if we react water with 1-propene in presence of sulfuric acid, it will give rise to 2-propanol. So water gets added as HOH, so hydrogen goes to the carbon which has more hydrogens, and OH goes to the other carbon. So this kind of addition is known as Markovnikov's addition. So a hydration reaction is a regioselective reaction. Alkynes also undergo similar hydration reaction with water. However, along with the sulfuric acid, mercury 2 salts are also used as a catalyst. So most common mercury salt used for this purpose are mercury 2 oxide and mercury 2 sulfate. And in case of alkynes also, this addition is a regioselective reaction, and the product will be obtained by Markovnikov's addition of water across the carbon-carbon triple bond. So let's write an equation. For example, if we react propyne in this case with water, the catalyst will be sulfuric acid and a mercury salt, for example mercury 2 sulfate. So these two act as a catalyst, and the product again will be Markovnikov's addition, in which a pi bond from alkyne will break, such as this one, and water will get added across it. So our end product will be an alkene where the OH group is present at number 2 carbon. Now this kind of product is known as enol. Enol is a organic compound which has an alkene group, such as here, and an alcohol group, ol. So en stands for alkene and ol stands for alcohol. Now, enols are not very stable molecules, and as soon as enols are formed, they will undergo rapid rearrangement, and it will result in formation of a ketone. So enols rearrange themselves into a ketone. So you can imagine this rearrangement to be uh, as if this hydrogen from here goes here and the double bond moves here. That's not the mechanism, but you can imagine the rearrangement to take place in this manner. So this rearrangement is known as keto-enol rearrangement. So therefore, hydration of alkynes will result in formation of a ketone. Although in the first step it will form an enol, but enol will eventually rearrange itself into ketone form. So we don't really get a hydration product per se, but this reaction still is a hydration reaction. Let's write the mechanism of addition of water to alkynes. In step number 1, as usual, the pi electron of a triple bond act as a nucleophile, and the step 1 involves the attack of nucleophile to the mercury cation, which act as an electrophile. And this will result in formation of a bridged mercurinium ion intermediate. Let's change this methyl group to hydrogen so that we have a terminal alkyne. Now, so this intermediate is known as mercurinium intermediate or bridged mercurinium ion intermediate. Second step involves the attack of water as a nucleophile to the bridged mercurinium intermediate, and this attack takes place at the anti-position. The reason is that the top side is already blocked by a large bulky mercury ion, so therefore a further attack from the top side of the double bond is not possible. So therefore water attacks from the opposite end of the bridge. Just as in the case of alkenes, the attack of nucleophile favors the carbon which is more substituted. For example, in this case, this carbon is more substituted. The reason is that in the resonance contribution, this more substituted carbon has a secondary carbocation character, which makes the intermediate more contributing. So therefore, the nucleophilic attack takes place at that carbon atom which is more substituted. In step number 3, the intermediate obtained at the end of step number 2 loses a proton in acid-base reaction where another water molecule acts as a base and a proton transfer results in the formation of a organomercury enol compound. This compound is called organomercury enol. As you can understand that it has a alkene as well as OH group, so hence it is an enol. In step number 4, organomercury enol undergoes the rearrangement. This rearrangement is known as ketoenol, and the name of this rearrangement is tautomerism. So it's known as ketoenol tautomerism. In ketoenol tautomerism, the enol transforms into ketone. And at the end, we will get organomercury ketone. In next step, the keto form of organomercury compound obtained at previous step undergoes a proton transfer process to form oxonium ion. Therefore, the keto form of organomercury compound obtained at the end of previous step undergoes a proton transfer reaction and this will result in formation of an oxonium ion. The loss of mercury from the oxonium ion will result in formation of another enol form. So this loss of mercury will result in formation of another enol. And finally, this enol form will undergo another tautomerism process, which will result in formation of a ketone. And this is the final step of our mechanism. Hydroboration followed by oxidation is another method in which water gets added to the carbon-carbon triple bond. So this kind of reaction has two steps. In first step, hydroboration takes place, and in the second step, we conduct oxidation with hydrogen peroxide to get the hydrogen product. So in the first step, borane adds readily to the internal alkyne to give us a trialkenylborane addition product. This addition is sin stereoselective. As we saw in case of alkenes, each borane will add to 3 molecules of alkyne here. So let me explain this process in a little bit more detail. As we saw in case of alkenes, borane aligns itself next to the pi bond, and hydrogen and pi bond breaks, and new bonds between carbon and hydrogen and carbon and boron will result in formation of a addition of boron across the carbon-carbon triple bond. Now there are a couple of things which should be noted. Once one boron is added to the triple bond and we get the product, although there is another pi bond available here, but another addition of boron does not take place. Or in other words, this addition and to get the di-substituted boron addition is not possible. It does not take place. So therefore, this does not happen, and we only get a mono boron substituted product in this reaction. So another hexyne will get added to the same addition product. Remember, one boron adds to 3 alkynes. So right now we have only 1:1. So the second hexyne will, I don't have enough space, so I am going to squeeze it here. So just remember, second hexyne so this is another hexyne molecule. So the second hexyne molecule will get added here, and we get a di-substituted boron. And eventually another similar reaction will take place and we will get a tri-substituted boron. So these R group represent that the same alkyne has added 3 times. So that's why it's called trialkenylborane. The enyl part shows that there is a double bond present in the added group. And remember, this is not exactly the mechanism which I'm trying to show here. I'm just explaining the process, what's happening here. So if you okay, so that's not exactly the mechanism. I'm just trying to explain that how 3 molecules of alkyne adds to one single molecule of borane. We just learned that in case of internal alkynes, only one of the pi bond breaks and boron adds only once and the other pi bond remains intact. However, if instead of internal alkyne we use a terminal alkyne such as propyne, in that case if we conduct the hydroboration process, both the pi bonds will break down and we will get a dihydroboration product. Dihydroboration product means that we will get a alkane in which will have two boranes attached to the same carbon atom, and this will not lead to the desired product. So to prevent this kind of dihydroboration of terminal alkynes, it is necessary to use a sterically hindered alkyl borane. So the most common borane, sterically hindered borane used is disecondary isoamyl borane. So secondary isoamyl borane is shown here, and this group is known as secondary amyl group. So in this borane, two of the hydrogens are already been removed, so that's a normal borane. And in SiA2BH, two of the hydrogens are already replaced by isoamyl group, which makes it sterically hindered from this side. Only one BH bond is available. So the advantage is that in this case, if we use this a terminal alkyne, then only one boration step will take place because of these bulky groups. Its borane is incapable of adding more than once, so it will result in only monoboration addition product. And because of these bulky amyl groups, this addition is also regioselective. Boron with bulky group stays on the open end of the alkyne, and hydrogen goes to the crowded side uh, of the alkyne. So in other words, hydrogen adds to the carbon atom which is internal to the alkyne, or the carbon atom which is more substituted, and boron is added to the carbon atom which is less substituted because of the steric hindrance caused by these bulky amyl groups. This addition is again a syn addition. Both hydrogen and the boron will be on the same side of the double bond. Treatment of an alkynyl borane with hydrogen peroxide in aqueous sodium hydroxide gives a product that corresponds to hydration of an alkyne. So after the first boration step, we get alkynyl borane, and then that product is treated with hydrogen peroxide in presence of sodium hydroxide, and we get a product which is similar to the addition of water across the carbon-carbon triple bond. So as you can see, it is similar to addition of H and OH. And we know that whenever OH group and a double bond is present on the same carbon, we call this kind of a compound an enol, and enols undergo a rearrangement process which is known as tautomerism. And in this rearrangement, enol changes to a ketone, so therefore this process is known as keto-enol tautomerism. Ketone is much more stable structure than the enol structure, so therefore equilibrium is shifted towards a forward direction or towards a ketone product. Although hydroboration oxidation reaction is a reaction which adds water across the carbon-carbon triple bond, but because of formation of enol at the end and enol undergoing tautomerism process, we get a carbonyl product at the end. We do not get alcohols. Depending on what kind of alkyne we start with, for example, whether it's an internal alkyne or a terminal alkyne, we may either get a ketone or we may get an aldehyde. Let me explain with the help of an example. So if we start with an internal alkyne, for example, hexine, this is 3-hexine. So in this alkyne, the triple bond is in the middle of the molecule, so that's why it's called an internal alkyne. So if we conduct the hydroboration reaction, so we have to use BH3 in the first step, and in the second step we have to treat it with hydrogen peroxide in presence of sodium hydroxide, and we know that the product will be addition of H and OH across the triple bond. So one of the pi bond, maybe this one, will break and we will get addition of H and OH across the triple bond. So this will be the addition product. Now in this case we have a enol. Let me just change the color so that we know that these are the new H and OH molecules which are added. So this is an enol, and we know enol will undergo a tautomerism process, and in tautomerism process the hydrogen from the OH goes to the adjacent carbon. This is not the mechanism, I'm just explaining the process, and the double bond shifts here. So that's the process, not the mechanism though. So therefore the product at the end will be a carbonyl compound let me draw it better. Okay, so just to preserve the zigzag uh, of the parent chain, I have to show the CO on the other side, but it's the same oxygen atom, so that's a keto form. So at the end we have a ketone, so this is 1 2 3 4 5 6, so that's a 3 hexanone. That's the name of this ketone. But instead of internal alkyne, if we start with a terminal alkyne, for example 1-hexine, so 1 2 3 4 5 and 6, so that's 1-hexine, and if we conduct the same reaction, remember in terminal alkyne we cannot use BH3, we have to use SIA twice BH, that's secondary isoamyl, and the second step is same, hydrogen peroxide followed by NaOH. we will get addition product similar to the first reaction. So that's 1, 2, 3, 5, and in this addition it's a and so it's a non-Markovnikov's addition, which means hydrogen goes to more substituted carbon and the OH goes to less substituted carbon. So this will be again our new enol, and this enol again will undergo a tautomerism process, and in that tautomerism process you will see that once we get the carbonyl compound, so 1, 2, 3, 4, 5, the OH, because the O is at the first carbon, so C double bond O will be at number 1 carbon, and hydrogens will get added to number 2 carbon. So this is an aldehyde. Okay. And of course we know that there is already one hydrogen here. So there is already one hydrogen here. So the point is that if we conduct hydroboration oxidation of a terminal alkyne, we get aldehyde at the end. And if we conduct hydroboration oxidation with an internal alkyne, we get ketone at the end. There are three types of reactions which can be used to convert alkynes into alkenes and alkanes. These reactions are catalytic reduction, hydroboration, protonolysis, and the last one is dissolving metal reduction. In this section, we will study all of these three type of reduction reactions. So let's begin with catalytic reduction. Treatment of an alkyne with hydrogen in presence of a transition metal catalyst such as palladium, platinum, or nickel converts the alkyne to an alkane. One such example of this kind of reaction is given here. 2-butene is treated with hydrogen in presence of either of these three metals will convert butene into butane. Catalytic reaction can be carried out at around room temperature with slightly elevated pressures. Reduction of an alkyne occurs in two stages. In first stage, alkyne will react with 1 mole of hydrogen in presence of catalyst, and alkyne will convert into alkene. And in second stage, alkene will react with 1 more mole of hydrogen gas in presence of catalyst, and we will get alkane. Although alkenes are produced during this reduction reaction, however, in most of these catalytic reduction reactions, it is not possible to stop the reaction at alkene stage. Hence, alkene cannot be isolated in catalytic reduction reactions of alkynes. Alkynes will always go directly to alkanes. However, by careful choice of catalyst, it is possible to stop the reduction after the addition of 1 mole of hydrogen. One such catalyst is Lindlar's catalyst. Lindlar's catalyst consists of a finely powdered palladium metal on a solid calcium carbonate. So this combination of palladium metal powder on solid calcium carbonate is known as Lindlar's catalyst. Reduction of alkynes over a Lindlar's catalyst is stereoselective, and the product obtained is a cis alkene. So hence the reduction of alkynes using Lindlar's catalyst stops at alkene stage, and the addition is a syn stereoselective addition. Therefore, the end product will always be a cis alkene. The mechanism of this catalyst reduction reaction is similar to the one which we studied during the reduction of alkenes using the transition metal catalyst. Earlier during the hydrolysis reaction with hydroboration, we learned that internal alkynes react with borane to give trialkenylborane. Treating a trialkenylborane with a carboxylic acid such as acetic acid results in a stereoselective replacement of the boron by hydrogen. So this boron will be replaced by hydrogen. And this process results in formation of a cis alkene. So the net effect of this reaction is a reduction of alkyne into alkene. Thus, hydroboration, protonolysis, and catalytic reduction over a Lindlar's catalyst provide alternative schemes for conversion of alkynes to a cis alkene. The metal catalyzed hydrogenation is not a suitable method because in that reduction alkynes convert directly to alkanes. However, Lindlar's reaction and hydroboration followed by protonolysis are a suitable reactions to convert alkynes to alkenes, and in particular cis alkenes. We just learned that Lindlar's catalyst and uh, hydroboration followed by protonolysis are suitable methods to convert alkynes to cis alkenes. On the other hand, dissolving metal reduction reaction is a process in which alkynes can be converted into trans alkenes. In this reaction, reduction is carried out with either sodium or lithium metal in liquid ammonia. In this reaction, the alkali metal acts as a reducing agent, and in this process, the metal changes into metal cation. And metal cation dissolves as a metal salt in the solvent for the reaction. So hence, this reaction is known as dissolving metal reduction reaction. So reduction by sodium or lithium in presence of ammonia, liquid ammonia, is also stereoselective, and reduction results in addition of hydrogen atoms in antiposition. So hence the alkene which is formed as a result will be a trans alkene. The stereoselectivity of this reaction can be explained by the reaction mechanism, which we will learn in the next slide. In the first step of dissolving metal reduction reaction mechanism, a one electron reduction of alkyne will result in formation of alkynyl radical anion. Now, what is alkynyl radical anion? It is an anion in which an unpaired electron exists on one carbon and a negative charge exists on the adjacent carbon. For example, if we start with this alkyne, a hemolysis of the pi bond will result in the cleavage of pi bond in such a way that one electron moves to one carbon, the other electron moves to the other carbon. Notice the use of fish hook arrow. Uh, this arrow represents the movement of a single electron. Sodium metal provides another electron which results in formation of a pair of electrons on carbon number. Uh, let's call this a star carbon number. This reduction by sodium will result in formation of alkynyl radical anion. So this is alkynyl radical cation. Excuse me, radical anion. This anion is resonance stabilized and it has another uh, resonating structure, so in which the negative charge changes from one carbon to the other carbon. So these are the two contributing resonance structures, and in this reaction we also get a sodium cation. The resulting alkynyl radical anion is an extremely strong base and it extracts one proton from the ammonia. So in step number 2, a proton is transferred from ammonia to the radical anion because radical anion is a strong base. So this process will result in formation of alkynyl radical. Notice this radical has no negative charge. So neutral species with unpaired electrons are known as radical. So therefore this is an alkynyl radical. In step number 3, another one electron reduction of alkynyl radical which was formed in previous step will take place and it will result in formation of alkynyl anion. So the radical which was formed in step number 2 will undergo another one electron reduction process, and that one electron reduction will be facilitated by this alkali metal. So this donation of electron, because it's a single electron, so it should be represented by a fishhook arrow or half arrow, and This will result in formation of a sodium cation because it donated its electron, and a formation of anion because now this carbon has a pair of electrons. This step establishes the configuration of the alkene, which will form in next step. As you can see in this pre-alkene, it has a trans geometry. The reason is the trans-alkenyl anion is more stable than its cis isomer. So therefore, after the sodium metal transfers its electron to form the anion, it adopts the trans geometry. A second proton transfer reaction completes the reduction process, and it results in formation of a transalkene. So proton is donated by ammonia as it was done in step number 2, and our alkenyl anion accepts a proton and we get a trans alkene. In this chapter, as well as in previous chapter, we learned how to prepare a desired organic compound starting from some other organic molecule. For example, in the beginning of this chapter, we learned strategies to prepare internal alkyne as well as terminal alkynes by starting from acetylene. We also learned various reactions such as hydroboration, reduction, or oxymercuration, and by applying those reactions, we can convert alkenes or alkynes into alcohols or carbonyl compounds or even alkanes if we want to. So all of those reactions are part of strategies for organic synthesis. So organic synthesis is generally the most important objective of organic chemists, and it is applicable to the preparation of compounds for use as pharmaceuticals, agrochemicals, plastics, or many other important materials. A successful synthesis must provide the desired product in maximum yield. Yield is important, and we should have a maximum control of stereoselectivity and regiochemistry, because many times the desired product, only one of the stereoisomer is the desired product. So therefore we want the control of stereochemistry. So we would want to make only single stereoisomer. We don't want to make the mixture. And a successful synthesis must also do minimum damage to the environment. So those kind of syntheses are known as green synthesis. So in this section, we will learn how to develop an ability to plan a successful synthesis. The best strategy is to work backward from the desired product. First, we will analyze the target molecule, and then we work backwards, and we will figure out how this target molecule can be synthesized from any particular starting material. While designing an organic synthesis reaction, we analyze the target molecule in the following ways. Remember, target molecule is the one which we want to synthesize. So first we count the carbon atoms of the carbon skeleton of the target molecule. We need to know how long should be the carbon-carbon chain in which we want to synthesize. So determining how to build the carbon skeleton from this available starting material is the most challenging part of the synthesis. If our starting material has same number of carbon atoms as in the target molecule, then we are good. Then we don't have to worry too much about it, because keeping the same length of carbon skeleton is easy. But if we must increase the carbon skeleton, then we need to use the alkylation of alkyne anion method, the one which we learned in this chapter. So alkylation of alkyne anion with primary alkyl halide is important method to increase the carbon-carbon chain length, one of the most important reaction. Secondly, we analyze for the functional group. So we need to know what kind of functional groups are needed in the desired product in the target molecule. And so for functional group, we must know what they are, how they can be changed to facilitate formation of the carbon skeleton, and how can they then be changed to give the final set of functional groups in the desired product. Regiospecificity and stereospecificity are also important considerations in this analysis. So once we analyze the target molecule, we know how many carbons are needed in its skeletal structure, and we know what kind of functional groups are needed in the target molecule. Then we work backwards and we plan for the starting material which will be capable of giving us that target molecule. So after the analysis of target molecule is complete, then we work backward. Surprisingly, it is often easier to identify the last step in a synthesis rather than trying to start from the beginning. And this process is known as retrosynthesis. So retrosynthesis is a process of reasoning backwards from a target molecule to a set of suitable starting materials. The idea is to start with a product structure and work backward one step at a time until we reach a point at which we can create our own synthetic intermediate from the starting material. If we cannot do this using our first proposed route, then we try working backward again and come up with another route. Organic synthesis is a creative process. There can be multiple routes to prepare same organic desired target molecule. To be good at synthesis, we must first be familiar with all the reactions, and we must know how to carry out those reactions in given set of conditions. So once we master all kind of organic reactions and we know their mechanisms, designing organic synthesis can become really easy and a fun exercise. So now that we know what is organic synthesis and how to design a reaction to prepare a target molecule, let's put our knowledge to practice. So in this section, we will design an organic synthesis starting from readily available material, and the readily available material is ethine and any alkyl halide, or alkyl halides are also known as haloalkanes. Okay, so I can use any of these two materials, any haloalkane and acetylene or ethine, and I need to synthesize this target molecule, cis 3-hexene. So let's think about it. So first thing we need to do is we need to uh, count how many carbons are needed in our target molecule. So let's draw its structure. So cis 3 hexene. So everything is important. So that's number 1, number 2, number 3. At number 3 position we have a double bond. And number 4, 5 and 6, and it, because it is a cis, so therefore hydrogens are on the same side. So this is our target molecule. So this is cis 3 hexene. Now rather than thinking about what I'm gonna choose to begin with, that's not a good strategy. So we're gonna apply the retro synthesis analysis. So retro means we just think about the one step before the final desired product. So I know that this can be made from a reduction of alkynes, right? So if alkyne, if I have some alkyne and I reduce it, alkynes can be reduced to alkenes. However, if I use, now what kind of reduction to use? Can I use the hydrogen in presence of metal or catalytic reduction? No, because we know that catalytic reduction will convert alkyne directly to alkanes and not gonna give us alkenes. So that's not gonna work. So what other reduction is available? So other reductions which are available are the Lindlar's, right? So Lindlar's can reduce alkyne to alkenes, and the dissolved metal that can also give us the alkenes. Now, but if we think about it, Lindlar and dissolved metal, there are a difference between them. The dissolved metal reduction give us trans alkene at the end, but our target molecule is cis, so dissolved metal will not work. So the reduction which will work is Lindlar's reduction. Okay, so now we know the step. And we know in reduction process, number of carbon atoms do not change. So it means now we know what we need here. So it means we need here hexine, 3-hexine. Right? So 3-hexine with Lindlar can give us this target molecule. So we established one step before this target molecule. So we would need 3-hexine. Okay, so let's draw 3-hexine. Okay, but 3-hexine is not our starting material, so we cannot start from 3-hexine because 3-hexine is not available to us. So it means now we need to learn how to prepare 3-hexine. How can we prepare 3-hexine, right? So 3-hexine is a internal alkyne, right? So it means if we break this hexine here, right? We can prepare this with the uh, with the alkylation anion reaction from this one, because and because in the beginning of this chapter we learned that the internal alkynes can be prepared by the terminal alkyl anions. So it means that if we have an anion this side, anion, alkyl anion, and this alkyl halide, we can prepare this molecule. Uh, so this alkyl halide is available, but this alkyne may not be. So in that case, we can also prepare this one by connecting at this point, because now we have acetylene part which is here, and these two sections can come from the alkyl halide. Okay, so now retroselectively I have figured out how to synthesize it. It may not be that clear with my reasoning yet, but I will explain it in the next slide how to design the reaction, and then it will be more clear. Okay, so what I'm proposing right now here is that 3-hexyne can be prepared from this plus this, X here and Y here. So these two can go out and we can prepare 3-hexyne, right? However, it means now we need to have this component. This can come from the haloalkane, so that we have, and we need to have this terminal alkyne. We don't have it, but we can prepare this one from this and acetylene. So okay. So now we have kind of designed the retroselectively. We started from the last step and we went backward, backward, and backward. So this retro synthesis strategy is complete, but now let's put it into practice, because we did not show any the real reaction step yet. So let me write this reaction in detail, because it looks messy at this time, but when I write the reaction it will become more clear. Okay, so our starting material is acetylene. So this is our starting material. Remember, we want to prepare cis 3-hexene. That is our target molecule, right? Okay, so first we need to make a bigger terminal alkyne. So bigger terminal alkyne can be prepared by this reaction. Remember, any haloalkane is available. So strong base, will produce this alkyl anion, and then we will add a alkyl halide, and I'm not going to write the mechanism, but just to show you, this goes here and Br leaves, and now we have a longer alkyne, right? So this was the longer terminal alkyne which was needed. Okay, so now this longer terminal alkyne will be reacted with a strong base one more time, and we will get alkyl anion again, and we will react it with another. So right now we have, let's count the carbon atoms. So 1, 2, 3, and 4, and the triple bond is already at number 3 position. Remember, we need to go to 6 carbon, so it means we need to add 2 more carbon atoms. So therefore we will add, okay, so this attacks here, Br leaves, and we will get our internal alkyne now. I'll keep the color same so that you see how we are adding carbons to the chain. All right, so now we have synthesized successfully our 3-hexyne. This is second to the last step. All we need to do is now reduce this using a Lindlar's catalyst. And remember, Lindlar's reduction is hydrogen in presence of palladium powder, which is coated on calcium carbonate. So that's the Lindlar's catalyst, by the way. As long as you write Lindlar's reduction and hydrogen gas, that's good enough. And this will reduce it to cis. So that is cis 3-hexene. And this was the desired product. And now we know the entire synthesis scheme starting from the available starting material. That we conclude chapter number 7. In this chapter, we learned various reactions of alkynes. We also learned the method to prepare alkynes. One of the most important reaction which we learned in this chapter was the alkylation of acetylide anion, because that reaction enables us to increase the carbon-carbon chain length in any chemical reaction. We also learned how to convert alkynes into carbonyl compounds and alkynes to alkenes or alkanes. And at the end of this chapter, we discussed about what is a retrosynthesis strategy and how to design any organic synthesis reaction if a common starting material is given. Thank you for watching. If you have any question, please contact me. Have a wonderful rest of the day. Bye-bye.